So hello everyone, I welcome you again in this lecture. In this lecture we are talking about analyzing the running time of recursive program codes. In the previous lecture we talked about how to analyze the iterative codes. So in this video we will see that how we can do with the recursive programs. So if you have not watched that video, so I advise you to first watch that video because I am going to take some of the results that we have already evaluated in the previous video. Okay, so let's start. Okay, so in this you will see that how we can evaluate our algorithm when it is represented using a recursive approach. We know that a problem can be either represented using an iterative approach or a recursive approach. We already discussed how to evaluate the running time if our problem is represented using iterative approach. You might be wondering that there are only two ways possible to represent the algorithm. Yes, we have two ways are there, and if it is not iterative, not recursive, then there is no need to identify or evaluate the running cost. It will obviously a constant cost. Now we'll see that how we can evaluate a recursive approach. So we have three basic approach, or you can say the ways to evaluate our algorithm. One is called back substitution method. Now, before we start and talking about these methods, let us recall that what are recursive approach. Recursive approach are the approach where we are defining our recursive functions, and the recursive function, you can say recursive function is a function which call itself. So whenever you make a function, this function is doing some logic. Inside the logic, we are making a call to the function itself. Now, the nature of the recursive function is the function is calling itself. This is the one point. And second point is every recursive function must have an exit point. It must have a termination condition. Otherwise, you are into the infinite loop. So you need to always keep in mind that what is the exit point, what is the termination condition, so that you can after making some recursive loops, you will be out of that loop. Now in the recursive approach, normally you will find we have two approaches. One is a dividing approach, one is a subtracting approach. What does it mean? It means we start with problem n, and when we make a function call which actually call itself, it is reducing the value of n. So let's say when you start with 10 values, next time when you call your function again, you may be calling with 9 values, and then with 8 values, and then with 7 values, and so on. Means you keep on decreasing. So this is called subtracting function. The other way is you have n values, you have n inputs, and next time when you make a recursive call, you are passing with some division. Means let's say you are saying n by 2. So initially we have 10 values. Next time when you make a call, it will be 5, then maybe 2, and then maybe 1, and so on. So this is of dividing nature. So this is a general behavior. You may observe that most of the time when you write the recursive function, either you are using dividing approach or a subtracting approach. Okay, so we have three basic methods of um, evaluating the recursive algorithms. One is the back substitution method. When we write the algorithms, we represent our algorithm in terms of function, and then we evaluate that function. So here also, when the very first thing is you must have an algorithm which is represented using a recursive approach, and then we need to represent that approach in terms of some mathematical function, and that function need to be evaluated for its running time. So in the substitution method, what we are doing, we are representing the function, and then we are substituting its subcomponents that is actually visible in the function. What does it mean? It means, let's say our function is defined by this function we are calling as t of n. So t of n representing a function which actually also represent the running time. So t of n equals to, let's say, some constant plus t of n minus 1. This is how we are representing our given function. So in the back substitution method, what we are doing, we keep on replacing the term which is actually a call of itself. So here we have n minus 1, so we will substitute the value with n minus 1, and similarly then we have n minus 2 and so on. So we keep on substituting the value till we exit from this algorithm, till we stop, and we will evaluate this mathematical kind of calculations to get the runtime of the given function. In the recursive tree method, whatever the function is given to you, we will make an recursive tree out of that, and then we will start from the root and we keep on extending the tree by making the branches, and then we will find out that while extending the tree by making the branches, what is the cost incurred. So from the root to the leaves, whatever the branches we have keep extending, we will calculate the cost at each branch, and that will give the total running time. Then we have Master's theorem. In the Master's theorem, we have some standard results that we are using directly to find the running time of our algorithm. So let's see one by one. In this video, basically we are talking about the back substitution method. In the next video, we will talk about recursive method, and then the next we will be talking about Master's theorem. So we'll take some examples to understand in a better way. Okay, so this is our first example. Let's say this is the algorithm for any problem, and we are presenting our algorithm with this kind of steps. We call it a pseudocode. So here we have one function which takes one input size n, and here we have a condition: if n is more than 0, then we will do this, and if n equals to 0, you can say else if n equals to 0, then return 1. Okay, we are only assuming these values for positive values. Now, the very first thing required is we need to represent your algorithm in terms of mathematical notations. So we will thoroughly see what is the behavior of this algorithm, and then we represent in the mathematical format. We will make one mathematical equation, and then we will evaluate that mathematical equation for our running time. Now, if you look at this, here we are passing one value n, and here we have a for loop which is doing one task. So this is going to execute n number of times. So the cost of this operation is n. And here we have a recursive call. This is a function demo which is passed with size n, input size n, and here you are calling the function again by reducing the size of n by 1. So how we are going to represent this? So let's say I am going to represent my function with t of n. That means I can represent the entire algorithm as t of n. So if n is more than 0, then the value of t of n is n plus t of n minus 1. So this is how we can represent. And if n equals to 0, then we are going to get 1. This is a kind of exit condition. This is a break point, you can say, in our recursive call. So we need to call we need to actually evaluate this part. We will evaluate t of n equals to n plus t n minus 1, and based on this evaluation we will get our running time. Now we are using back substitution method. Now for all the representation, whatever the algorithm you are making, and then you are representing with any mathematical equation, this mathematical equation can be solved for running time using back substitution method, recursive method. Here in our in this video we are only focusing on the back substitution method. The same algorithms we will be solving in our next video by using the recursive tree approach. Okay, so let's see how the things will work. So in the back substitution method, we will look our main equation. This is our main equation, which is represented in terms of t n minus 1. So we need to substitute the values on which this main equation is actually represented. So it is represented in terms of t n minus 1. So we have to substitute the value for t n minus 1. And when we write t n minus 1, this is again represented into it constituent. So we will keep on replacing these values in order to reach to the exit condition. So what does it mean? It means, I mean to say, this is our main kind of equation which is represented for this algorithm, Tn equals to n Tn minus 1. So if I replace this n with n minus 1, what I will get? I will get Tn minus 1 can be written as n minus 1 plus T n minus 1. I have replaced n with n minus 1 minus 1. So what you get? You get n minus 1 plus T n minus 2. Now T n minus 1 is actually represented using T n minus 2. So how can I write T n minus 2? So T n minus 2 can be written as, I will replace n with n minus 2. So this can be Tn minus 3 and so on. So it's keep on expanding. When we keep on substituting, it's keep on expanding, and it will stop at the value when this becomes 0, means when this term becomes 0, then you will get 1. Okay, so we need to keep on expanding, but before we expand this further, we need to observe that what is the behavior. So the behavior is, when you write T of n, we have one nth term, and then we are making a recursive call in n minus 1. So similarly, when you write T of n minus 2, you have seen here, we have a n minus 2 term, and then it is calling recursively Tn minus 3. Now we have these three expansion. Now we will use these expansion in our original equation. So we have T of n plus T of n minus 1. Now I am going to replace T of n minus 1 from here. So what I will get? I will get n plus, this is n minus 1 plus T n minus 2. Now this term I can replace from here. So what I get? I will get n plus n minus 1 plus, now this I am going to replace from here, n minus 2 plus Tn minus 3. So this is how our equation is keep on expanding. Now we have only expanded up to 3 terms, Tn, Tn minus 1, Tn minus 2. So we have to keep on expanding like this. So instead of substituting for every term, we need to find out the pattern, the way in which it is expanding. So what we have observed, that in the third recursive call, we are getting the term n minus 1, n minus 2, and the recursive call for n minus 3. Similarly, if I keep on expanding, it will keep on going, and it has to stop when we get this term as t of 0. So let's say, after doing in such a way, at the kth iteration, at the kth recursive call, we got this exit point. So how we can going to do? So if this is n minus 3, so if I replace this with the k, then this will be k minus 1. So I am going to write n plus n minus 1 plus n minus 2 plus n minus k minus 1 plus t of n minus k. This is our general term. Now, to find out when this general term is going to execute, we need to get this term as t of 0, because at n equals to 0 we get 1. So replacing this term with n minus k is equals to 0, that means we get k equals to n. So we replace the value of k equals to n in this general term to see what we get. So if I replace this, so we'll get n plus n minus 1 plus n minus 2 plus n minus k. So I am replacing k with n plus 1 plus t of 1. So what you get? You get n plus n minus 1 plus n minus 2, and this will be what? 1 plus 1, n plus n minus 1 plus n minus 2, 1 plus 1. Now this, if you look at this, this is your series 1 plus 2 plus 3 plus 4 plus 5 plus and so on. So we can represent the series as n into n plus 1 by 2, and you can say this is also plus 1. Now one thing to remind that whenever we solve this equation, our objective is to find out the class to which it belongs. It belongs to a linear class, it belongs to a quadratic class, it belongs to a cubic class. So here we can see this is represented in terms of n square. So when you expand this, we will look to the highest order term. So highest order term is n square. So the running time is big O of n square, and this is the running time. So this is how we can find out the running cost of this particular algorithm. Okay, moving to next. Okay, this is the next example. This is another problem which is represented recursively, and our intention is to find the running cost of this algorithm. So here we have provided the input of size n, which in the next recursive call reduced to n minus 1. So we are representing our function with t of n. So t of n is basically representing the cost of this algorithm. So we are representing this function as t of n. Here we have this main body where you can see there is a loop for I equals to 1. It goes up to n, and it is incrementing with double value. It is not incrementing linearly, but it is incrementing with a double value, and we already discussed in our previous lecture that with this kind of code the cost is log n. And then we have demo t n minus 1, so we can also represent as a t of n minus 1, because when we have demo n we call it tn. So when we call it again with the size n minus 1, we can represent as a tn minus 1, and this is your exit condition. So you can write your equation as t of n is equals to log n, means the cost will be log n plus t of n minus 1 when n is more than 0, and when n equals to 0, then the cost will be 1. So this is how you can represent your entire function. So we need to solve this equation, we need to solve this function to find out the running cost of this entire algorithm. So let us see. So our function is let me write here t of n is equals to log n plus t n minus 1 when n is greater than 0, otherwise it is 1 when n equals to 0. So we are using a back substitution method. We already seen that how to work with this method. So we'll write our basic equation t of n equals to log n plus t of n minus 1, and then we substitute with the term which is used to define the main equation. So this is defined, we're using log n t n minus 1. So if I see how we can represent t of n minus 1, so in terms in place of n we can replace n minus 1. This is t n minus 2. So here it is represented using t n minus 2. So t n minus 2 can be represented using log n minus 2 plus t of n minus 3. So we have these two representation of its subconstituent of this equation. We can replace these values in the main equation. So I will replace t of n minus 1 with this value. So my main equation is t of n is equals to log n plus t of n minus 1. I am going to replace t of n minus 1 using this. So I get log n plus log n minus 1 plus t of n minus 2. Now I can replace t of n minus 2 from this equation. So I can write log n plus log n minus 1 plus log n minus 2. Now this equation is keep on expanding in such a way, so we need to identify what is the pattern, how it is going, how it is actually expanding. So we need to find a generic term. So if we keep on expanding like this, we will get, so you can see when we reach up to the third expansion we get n minus 3. That means if you go to the kth expansion you will reach up to n minus k, and when it is a third expansion n minus 3, the previous term is minus 2. That means if I am going to get the kth term, so I'll get log n plus log n minus 1. So I keep on expanding up to the kth, log n minus 2, and it will be log n minus k minus 1 plus t n minus k. This will be the kth expansion. Now we need to look to the exit point. So this is going to stop. Now what we have seen here, we keep on replacing this term. Now this term is going to stop when this becomes t of 0. So if this term is replaced with 0, then it is going to stop. This is the exit condition. So we need to replace n minus k equal to 0. That will give k equals to n. So we will going to replace k equals to n to get the answer for this equation. So what we will get, let us put this value. So we get log of n plus log of n minus 1 plus log of n minus 2. This will be log of 1 plus t of 0, which is again 1. So here you can use the log, you can use the concept of log. So we know that we can represent as n into n minus 1 into n minus 2 into 1 plus 1. So this, now here you can observe that this is a factorial term. This is n into n minus 1, n minus 2 up to n. So we will write it as log n factorial plus 1. And this term in the asymptotic notation is equivalent to n raised to the power n. So here you can say that this is actually big O of n log n. This is our running time for this kind of algorithm. Okay, moving to next. Okay, in the next question we have again a different algorithm which is represented again recursively. So here you can see this is our t of n, and we need to find out the cost of its components. So here this is our main logic, this is our exit condition. So here you can see if n is more than 0, then we need to execute one statement. This is a kind of cost is let's say 1, and then you are calling recursively with a size less with 1 less than the n. So this is t of n minus 1, t of n minus 1. So if I represent this equation, it is going to represent it like this: t of n, the cost is 1 plus 2 times t of n minus 1, and when n is more than 0. Otherwise, if n equals to 0, you get 1, and this is our exit condition. So let's solve this part. Is again you write here t of n equals to 1 plus 2 t n minus 1 when n is more than 0. Otherwise, when n equals to 0, it is 1. So again I am using a back substitution method. So let us write here. I hope now you understood how to evaluate by using back substitution method. We will write our main equation and then we will expand by the constituent term. So here we have we have tn minus 1. So tn minus 1 can be written as 1 plus 2 tn minus 2. Then we have n minus 2, so tn minus 2 will be written as 1 plus 2 tn minus 3. So we will use these two expansion and we will write in our main equation. So our main equation is t of n is equals to 1 plus 2t n minus 1. I am going to replace t of n minus 1 from here. So we get 1 plus 2, and t n minus 1 can be written as 1 plus 2t n minus 2, which is 1. So when you expand this, 2 into 1 is 2 plus 1 3, so we get 3 plus 4t n minus 2. Now again you will expand this using t n minus 2, you will get 3 plus 4, and this is 1 plus 2t n minus 3. This will give you 7 plus 8t n minus 3. So we need to find out a generic term, means if we keep on expanding this way, what will be the generic term. So let us understand that how the things are working. So here you can see this is 2. So we will represent this. So I can write this as uh, 2 power 2 minus 1 plus 2 square t n minus 2. So when we have n minus 2, here we have a multiple of 2 square, and this is 2 square minus 1. Similarly, I can also write this as 2 cube minus 1 plus 2 cube t n minus 3. Okay, so now we understood what is our general term. So if I am keep on expanding, I will get, this will be, if I keep on expanding uh, up to the kth, so I will get 2 power k minus 1 plus 2 power k t n minus k, and we need to keep on expanding until it reaches to the exit point. So here the exit point will be when this term becomes 0, means when we reach to t of 0, then only we'll stop and we'll get the value 1. So this n minus k must be equal to 0 to reach to the exit condition. So we'll write n minus k equal to 0. So k will be equals to n, and then we will put the value of k equals to n in this equation. So what we get, we will get 2 power n minus 1 plus 2 power n t0. So what you get, you will get here 2 power n, you can write this, plus 2 power n minus 1. This is actually t of 0 equals to 1. So I have written this term here, and 2 power n minus 1. This is 2 into 2 power n minus 1, you can write like this. Now our objective is to look to the highest order term, and that gives us our running time. So here this is big O of 2 power n. So I hope you understood this. So next we move to the next example. So this is our next example. We'll see here. We have again a recursive algorithm, but here we have used a dividing approach. In the previous case, we have called our recursive function where the size of n is reduced by decreasing the size by a factor 1, 2, or 3. But now here we are decreasing the size by dividing it with some value. So here we are dividing it by 2. So again, we will use the same approach. I am using a back substitution method. I am representing this as t of n. We need to find out the cost of the entire code. So here we have one message we are printing. Let's say the cost is here actually 1. It's just a constant cost. And then we are calling this function recursively, which can be represented as t of n by 2. So I can write my function as t of n equals to, the cost is 1 plus t of n by 2 when n is greater than 1, and otherwise this cost is actually 1 when n equals to 1. This is n equals to 1. So when n equals to 1, we will get 1. When n is more than 1, we have t of n by 2. One thing to observe in general, when we are doing a dividing approach, then we are putting the constraint as n is more than 1. when we are doing a subtracting approach, then we are using n is more than 0. This is just a general behavior. It's not compulsory, but in most of the problem you will see this kind of approach. So here, this is how we are representing this algorithm. Our objective is to solve this equation to get the running time. So let's move. So this is how we are representing. This is a t of n is equals to 1 plus t of n by 2 when n is more than 1, and if n equals to 1, then it will return 1. So this is our exit condition. So again, I am using a back substitution. We will use the same approach. Already we have applied this in the previous examples, so I am doing little fast now. So t of n by 2 can be written as 1 plus t of n by 4. T of n by 4 can be written as 1 plus t of n by 8. So I am putting these values in my main equation. So we have t of n equals to 1 plus t n by 2. I'll replace this value from here. I get 1 plus t n by 4. This will be 2 plus t n by 4. Now I will place this from here, and what I will get, 2 plus 1 plus t n by 8. So if we expand this, you will get 3 plus t n by 8. So this is how we keep on expanding. We need to find out our generic term. So here, if you try to make a general term, you will find here this is 2 square. Okay, so let me make a generic term. Okay, so I will say that this is actually 2 plus t n by 2 square. Okay, so when you have a square term, then you have 2 here. So here I can write 3 plus t n by 2 cube. Even you can write here, this is 1 plus t n by 2 power 1. So now we get our generic term. That means if I keep on expanding, I will get k plus t n by 2 power k. Now in order to stop, we need to look to the exit condition. So it will going to stop when you reach to t of 1. So t of 1 is actually 1. Now that means in order to stop, we need to make this term as equals to 1. So I am going to replace n by 2 power k equals to 1, which will give me 2 power k equals to n, or you can say k equals to log n. I am going to replace this value here. I will get here log n plus t of 1, which is log n plus 1, which is nothing but big O of log n. So this is my answer. Okay, moving to next. Okay, next again we have a recursive algorithm, and we have used a dividing recursive approach where the function is called by dividing the input size with some constant. So here we are dividing it by 2. So again I am representing this with the tn, and if n is more than 1, then this is a loop. So that means the cost of this is actually n, and then we can represent as t of n by 2, and this is our exit condition. So I can write this as t of n is equals to n plus t n by 2 when n is more than 1, and it will return 1 if n equals to 1. So this is our equation. Okay, let's see how to solve this equation. So our equation is t of n equals to So our equation is t of n equals to n plus t n by 2. Okay, when n is greater than 1, if n equals to 1, then it is 1. So I am going to write here t of n equals to n plus t n by 2, and then I keep on expanding. N by 2 will be n by 2 plus t n by 4, n by 4 equals to n by 4 plus t n by 8. Okay, so these two equations will be used in our main equation. I am going to substitute these values. So my main equation is t of n equals to, I am replacing this with this value, so n plus n by 2 plus t n by 4. I get n plus n by 2 plus t n by 4. Okay, replacing this with this, n by 4 plus t n by 8. So what we get, n by 2, n by 4, t n by 8. Okay, so by expanding up to 3 steps, we need to find out the generic term. So we will have a look into this and we'll try to find out. So here we can see that when we have t, this is n by 2. Okay, and then when we moved here, this is n by 2 plus t n by 4. Fine. That means I can also write, let me write like this, n by 2 power 0, n by 2 power 1, n by 2 power 2, and t n by 2 power 3. That means if I want to get the kth term, then kth term will be n by 2 power 0, n by 2 power 1, n by 2 power k minus 1 plus t n by 2 power k. So this is our generic term, and we need to find out at which point this is going to stop, and this is going to stop when this recursive term is going to become 1. So when n by 2 power k equals to 1, that means 2 power k equals to n, or you can say k equals to log n. So we need to replace this value in this equation, and what we will get here, you can replace, and also you can just take n common, so you'll get 1 by 2 power 0, 1 by 2 power 2, so on, 1 by 2 power k is n, so you can say here 2 power uh, k minus 1 plus 1. Okay, so here we have a kind of series, and this series can be easily solved. We have standard results. So just refer to this result. We have sigma I equals to 0 to k. If you write 1 by 2i. So if you look at this, so we have a standard result which goes from 0 to infinity actually. This is already given in the core man. And when you expand this series, so here you can see that the value of each term is going to reduce as you move to the infinity. And this is given as approximately 1. So I am going to replace this entire thing with 1. So what I will get here, I will get n 1 plus 1. So this is nothing but big O of n. So this is the answer for this evaluation. We have another recursive algorithm. Here you can see this is demo again called here, but its nature is different. Here we have called 2 times with the size just half of the initial size, which is n, and now it becomes n by 2, n by 2. And also, if you look at this in the main body, we have a for loop which do some task. So the cost of this operation is n, and this is a tn by 2, tn by 2, when we say that this is t of n. So we can write that t of n is equals to n plus 2t n by 2 when n is greater than 1, and when n equals to 1, then it is 1. This is how we are going to represent. So let's say, so let's solve this equation. So let me write first our equation is t n equals to n plus 2t n by 2 when n is more than 0, sorry, and when n is more than 1, and when equals to 1 you get to 1. This is how we are representing. So again, use the same approach. This is our main equation, main term of the given equation, 2t n by 2. We will find the other terms of this equation. N by 2 is n by 2 plus 2t n by 4, then t n by 4 is equals to n by 4 plus 2t n by 8. So we will replace these terms, n by 4, n by 2 in this expansion of this main equation. So let me write again t of n equals to n plus 2t n by 2, and now I am going to replace this term n by 2 from here. So I will write n plus 2 n by 2 plus 2t n by 4. This is going to give us uh, 2n. When you expand this is going to cancel. It will get 2n plus 4t n by 4. Okay, so when you expand it further, this term tn by 4 from here, you'll get 2n plus 4 n by 4 plus 2t n by 8. This will give you 3n plus 8t n by 8. Okay, so now we need to look to the general term. Also, you can write this. Now this is the third term. So here we have, you can see 3. This can be written as 2 power 3. So you can write as 3n plus 2 power 3 t n by 2 power 3. Also, you can write this term here as well. The second iteration, when you can write as 2n plus 2 square t n by 2 square. So we get our general term. That means if I keep on expanding, so our general term is kn plus 2 power k t n by 2 power k. So we know that it's keep on expanding like this, and it will stop when this term becomes equals to 1. That means when the t of n by 2k is actually becomes t of 1, then only you are going to stop, because this is the exit condition. So that means n by 2k should be 1. That means k is actually log n. This already we have seen. So we will replace this in this equation and see what we get. So you will get here n log n plus 2k is actually n, and this will be 1, n into 1. So you get here n log n plus n, which is actually big O of n log n. So whenever any equation is given to us, we just look to the highest order term. So here this is n log n is the highest order, and our answer is n log n. Okay, so we'll take the last example for discussion. Here I have just directly written our equation instead of writing the code, because already we have seen that how to convert the code into the equation. I have simply wrote here the equation of any problem, and now we will solve it. So what is required? Let's see. So let me write here equation, which is t of n is equals to c plus 2tn by 2 when n is more than 1, and when n equals to 1 it is 1. So let's see. Again we will use the same approach. This is our main function, t of n equals to c plus 2tn by 2, and we will replace this. Tn by 2 will be written as c plus 2t n by 4 . So I will be using these two expansion to solve our main equation. So my equation is t of n equals to c plus 2t n by 2. I am going to replace tn by 2 from here, and you get c plus 2t n by 4. And when you expand this, you'll get 3c plus 4t n by 4. Now again expand t n by 4 from here. 3c plus 4c plus 2t n by 8. So when you expand this, you get 7c plus 8t n by 8. And already we have seen that how we can find the generic term. So actually this is you can say this is 2 power 3 minus 1 c plus 2 power 3 t n by 2 power 3. That means if I go to my kth term, I will get 2 power k minus 1 c plus 2 power k t n by 2 power k. So again we know that it is going to stop when this term becomes equals to 1. That means when n by 2k equals to 1, it is going to stop. So we know that 2 power k equals to n. This means k is log n. So we substitute this value in this equation, and what you get, you will get 2 power k is n. So n minus 1c plus 2 power k is n, and this will be 1. So you'll get, so actually when you expand this, when you solve this, you will get this is big O of n. So we have seen many examples. Some recursive algorithms we have seen, and then we have also learned that how to convert these algorithms into equation form, and then how to evaluate that equation to find the running time. In the next video, we will be discussing about solving all these same algorithms using a recursive tree method. You must be knowing all these methods. Also, we have some more interesting results. Like if you observe this results, you can also find some pattern into it. So this is the recursive algorithm. This is the kind of equations given for any recursive algorithms. So let's say we have t of n is represented as c plus t n minus 1, or 1 plus t n minus 1, n plus t n minus 1. So if you look to the result, when this kind of equation you are having, when you have a constant plus t n minus 1, then the result is big O of n, means the cost of this kind of function is big O of n. If it is a constant or if it is a 1, then it is big O of n. Actually 1 represent the constant here, so I have written one value here, but actually it represent some constant effort. Now whenever you have your representation in this form, n plus t n minus 1, so what you have to do is, whatever the term you are adding into this equation, you simply multiply that term into your standard term. So here we have n, and when you have one more term n in this equation, so you have multiply n into n, you get n square. Similarly, if you have n square here, so you can multiply this n square into your standard term, that is n square into n, you have n cube. Similarly, here you can see n log n. So this is just an observation. It will help you to check your answer. So if you have any question and when you are solving it, if you have this kind of properties in mind, you can self verify that your answer is correct or not. So if your equation is of the form n squared tn minus 1, or let's say if your equation is of the form tn equals to n cube plus tn minus 1, that means your answer will be big O of n power 4. So you can also self test that your answer which you are getting is correct or not. Similarly, if you look here, here we have no multiple factor with the t. Now if you have this multiple factor like 2 3, so if you have this kind of factor associated with the recursive term, so here we have recursive term where the factor is actually 1 in all the cases, but now we have 2 3. So if it is associated, then your answer will be in this form. You can take this for raised to the power, and then this will be the base term. So 2 power n. If it is 3, this becomes 3 power n. With constant, there is no other term is required, but if it is n, then you will get, this is 2 here, so n into 2 power n. Similarly, you can see here log n into 2 power n. So if you understand the pattern, it is good. If you don't understand this pattern, then there is no problem, because I believe if you follow these steps what we have discussed, definitely you will get the correct answer. So this is all for this video. In the next video we will learn how to find or you can say how to analyze the running time using a recursive tree method for any recursive algorithm. That's all for today. So take care and see you in the next lecture.